The next segment depicts random pinhole formation. The bubble you see initially is not on the chip, but is entrapped in the paste. As the chip enters the paste, it traps this bubble and pulls it out during withdrawal. Notice this bubble actually displaces the classic pinhole somewhat. This is better illustrated in slow motion. The knowledge that pinholes are caused during insertion suggests, unlike the cavitation theory, these bubbles could be squeezed out by allowing the capacitor to hit the bottom of the paste reservoir. Indeed, these bubbles are forced from the end of the capacitor, but remain nearby. Unfortunately, the bubbles are pulled back to their normal positions as the capacitor is withdrawn from the paste. Now the insertion rate will be slowed. The wetting front starts at one corner and wicks across the surface, excluding all bubbles. It is also important to notice no cavitation bubbles are formed upon the quick withdrawal. To show consistency, the last experiment was repeated. The last experiment, run in slow motion, shows very clearly the wetting front starts at one edge and spreads to the opposite side with no bubbles formed. A number of important and practical conclusions can be made. Classic pinholes are caused by air bubbles entrapped at the termination paste surface. The good news is classic pinholes can be prevented by slow insertion of chips into paste. Chip withdrawal rate does not prevent classic pinholes. Chip withdrawal rate and bottom delay times do affect termination coating thickness and edge band straightness. Literature references cited are shown here.